forgot my iPad. We're going. Let's see if we can break our phone. Okay. This is not a good day to. Good, good, okay, real, oh, that's good.
Like actually, yes.
Okay, awesome, awesome. Okay, guys, let's stand up, Okay, my phone's not gonna drop back there. It does, okay. Okay, today is like, I think conceptually the hardest day of the entire course, so let's sit back down. Today is kind of conceptually the hardest day of the entire course. Because we're moving into a new section, and this new section is quite a bit more challenging than chapter 13, which I know you don't want to hear. Okay, but that is the reality of Calc 3. When I say R of t, you say space curve. Yeah. When you say, could you sit here? My phone's gonna break. I know it's gonna. Sorry. Yeah, when I say R of t, you say space curve. Okay, it's a ordered triple. It's a vector valued function, which is an ordered triple of 3 real valued functions. Okay, and when I say function, what's the definition of a function other than I hate you, Dr. Warren? Okay, what's the definition of a function? For like the 5th time, I mean, we take integrals, derivatives of functions, limits of functions. What's a function? Relation that assigns to each element in one set called a unique element in the second set called the range. And we go back to high school, it's not so bad. I'm looking at this and I ask, does that represent a function? Does that represent a function? And you're like, yes, it passes the vertical line test. So like, for example, if I have some domain here, I pick an x from here, I go up and go over, hit the function, there's f of x in the range. Is there only one f of x? Is there only one f of x for that x? So it meets the definition of what it means to be a function. And then we kind of exploited that over here because in this case we have 3 real value functions which create our vector value function. But if I really think about it, R as a function takes t from the real numbers, just picks a t between like 3 and 7, but it gives me, when I'm said and done, I get an ordered triple of 3 real numbers, which makes it a vector. So my range is the set of vectors. My domain is the real numbers, but my range is a set of vectors. And so what we're saying here, to meet the definition of a function, for every real number, I'm only going to get one and only one. For every real number, I'm going to get one and only one vector. And then it meets the definition of being a function. And so, like, for example, when we were talking about our space curves, I'm being lazy. Maybe that's my space curve, t squared t cubed d to the t. That's r of t. For every t, will I only get one vector? For every t, will I only get one vector? You're like, yeah, Dr. Warren, because this is a function, and that's a function, and that's a function. Now this is what chapter 14 is about, and this is why it's so much harder. We kind of flip it around. If I think about most scenarios, if I think about most real applications of mathematics, think about your science classes, your engineering classes. If you think about most applications, doesn't the result depend on more than one thing? Like if you're studying heat on a plate, doesn't it depend on more than one thing? Doesn't it, like, I mean, it depends on time, doesn't it depend on time? But it also depends on where you're at on the plate. It could be hotter or colder, depending on where you're putting that source. If you're watching a wave, it depends on time, but it also depends on where the wave is. The taste of a cake, does it depend more than just on flour? Does it depend more than just on flour? Okay, voting. Okay, does it depend more than just on wanting to vote, or more than just one thing as far as what's going to happen in this election? Okay, so everything depends really on more than one thing. And as far as physics is concerned, I mean, really all we've done through high school and through Calc 1 and Basic 3 through Calc 2 is be thinking of functions that only depend on one variable. Time, if it's physics. And we kind of upped it here. And we said, okay, yeah, instead of just having one function, we're going to think of three functions. But if I think about real applications, my function, whatever it could be, likely is not just going to depend on x, but could depend on y, some other variable, could probably depend on a z, and we're running out of letters. Could it depend on more than that? Could it depend on more than that? And in this class, I kind of say this. If we can't understand it with 2, are we kind of done? I mean, if we don't understand it with 2, it doesn't really make much sense to go to 12. Okay, so we're going to hug pretty close in this class to just looking at functions that are functions of x and y. Just looking at functions that are kind of like f of x and y. The book also focuses a lot of time on x, y, and z, and sure, you're going to need that, but I'm not going to focus so much on it. I'm going to focus primarily on f equals a function of x and y. Now say why, Dr. Warren? Okay, because if I look at this, my domain is three-dimensional. I mean, here, okay, my domain is one-dimensional. My range is one-dimensional, and to plot it, I get a two-dimensional object. Okay, so here, my domain is two-dimensional. My range is one-dimensional. So I used up all my x, y, z's. I used up all my x, y, z's by then. Here, my domain is three-dimensional, so a domain in three-dimensional space. This is the domain. These are the values you would plug into the function. Might look like a potato. Mr. Potato Head sitting here in three-dimensional space. You pick an x, y, z, that goes into your function. Now where's your other axis? Do you see how hard it is to plot? How many people will see real well in 4 dimensions? How many people will see real well in 4 dimensions? How many people like living in 3 dimensions better? How many people visualize? You're like, I don't really like 3 dimensions. Space curves, I suck. You know, most of us. We love this, and the only reason is because we don't introduce 3 dimensions early enough It should be taught in high school. It would make it so much easier if it was taught in high school. Okay, so we're going to live here, and so go ahead. We're going to live here. I'm thinking of z being f of x, y. Give me a function of x and y. Give me a function of x and y. Just go ahead. Give me a function. Give me a function of x and y. Go ahead. Give me a function of x and y. Like, Dr. One, what the hell are you talking about? Well, it's going to depend on, I know this is hard. It's going to depend on x, and it's going to depend on y. So, like, for example, e to the x times y. E to the x times y. Maybe plus x squared divided by y. Is this a function of x and y? Is this a function of x and y? Okay, so now let's just try to evaluate the function at a point. So give me an x and a y, a real x and a y.
0,
0,
0.
0. Okay. Michael picks 0, 0. Find the z values, because we're going to be thinking about this. Find the z value. Find the z value. And you're like, Michael, you would get a 0 squared, and then you would get a
1.
e to the 0 times 0, which is 1, and then you get it divided by 0, so you get 1 over 0. If it was 0 over 0, would you have a shot? Thanks, Trevor. If you had a 0 over 0, would you have a shot? And the answer is yes. But a 1 over 0, you know that does not exist. And you're like, well, what does that mean, Dr. Warren? Did I pay you to pick that point, Michael?
No.
No, I didn't give him $1. I should. If I had $1, I'd give you $1. Okay, so this means, and you guys think this is going to go away, I can tell already, as you got, I can look in your eyes, you're like, you have no idea how bad today's going to get. I do. The students leaving with those like beaten looks on their face. It looked like this when I wrote down the definition of limit for these things. This is the way it looked in my first class. The kids that kind of knew to be afraid, it was as if I was driving through my neighborhood. For some reason, they will not kill the deer in my neighborhood. I live in the city, okay? There's 30 deer living in my neighborhood, eating my shrubs. I live like literally 10 feet from I-81 in Harrisonburg. Every night I drive home, and I've got to flash my high beams because I'm just afraid a deer is going to jump up into my car. And then one night, last night, well, the night before, one did. I didn't hit it, thank goodness. I'm just prepared for it. But that deer looked like this to me. I mean, it was like this. And when it saw my headlights, it was just like that. It was just like that. And that's the way it looked in this class just a little bit ago. The kids I thought, this is going to go away. They were just like, I'm going to zone, I'm going to zone, I'm going to zone. The ones were like, is he going to hold us accountable for this? Do we have a quest next week? And is he going to hold me accountable? Do we have a quest next week? Yes. Yeah, next Friday. Will this be on it? Yeah, this will be on it. And you're like, okay. And then still you'll zone and say, seriously, that's impossible. Okay, so now here we go. What does it mean when Michael's point didn't work? What did it mean when Michael's point didn't work? Well, that means the ordered pair 0, 0 ain't an element of the domain. That means Michael's pair, ordered pair 0, 0 is not an element of the domain. You're like, well, Dr. Warren, what do you mean the domain of this thing? Well, the domain depends on how many variables. The domain depends on how many variables. I know this is hard. And we have a
X.
and we have a y. When you another x. We have a y, okay? So how many variables does the domain depend on?
2.
2. So if I'm thinking about what the domain looks like, we've got to draw ourselves an x, y, z. This is the which axis? This is the which axis? X. This is the y-axis. So we're talking about points down here on the floor. And we're asking, what points on the floor can't we evaluate this function at? What points on the floor can't we evaluate the function at? And you're like, well, Dr. Warren, You don't want any points on the floor where y would be
0.
0. You don't want any points. The domain is going to be y is not allowed to be 0. Well, what are all the points on the floor where y is 0? What are all the points on the floor where the y coordinate is 0?
On the x-axis.
On the x-axis. So my domain for this function, everybody's fine over in here and back there, here, there, but nobody on that line can go into the function. Does this make sense? Does this make sense? Nobody on that line can go into the function. So let's actually pick a value. Let's actually pick a value that is in the domain. So Nick, give me a value that is in the domain of the function. Right, so there's going to be 2 of them. For 6. Can you find the z value, guys, that corresponds to Nick's point 4, 6 for this two-dimensional function e to the xy plus x squared y? And you're like, Dr. Warren, do I have a calculator? No, we'll just leave it. We'll just leave it. So you guys should be done. It should be what's in the bottom, what's in the bottom, what's in the bottom, what's in the bottom, what's on the bottom. 6. Stop it, Dr. Warren. What's on the top? What's in the numerator? What's in the numerator? E to the 24. And you're like, ooh, big number, big number. And then
Plus 16.
plus 16. How many people got that? How many people at least understand that? Now ask me, what does that mean? What does that mean graphically, Dr. Warren? Well, it means if I go out 4 along the x-axis, and I go out
6.
along the x-axis, and I look at that point 4, 6, is it in the domain of the function? Is it in the domain of the function? So now, let's go back to high school. I pick a point in the domain of the function, like, for example, 4. I plug it into the function. Where's f of 4? Where's f of 4? Most kids don't come into my class knowing this. But how do you find f of 4? You would go up and then over. So there's f of 4. Then this point on the graph of the function contains both the domain and it contains both the domains. So it would be, you'd go over 4, you'd go up f of 4. And so that would be a point on the domain of the function. Now here we're saying z is equal to this number. So we're saying that we pick 4, 6 in the domain, and then we shoot straight up. Now guys, I'd have to be Superman to plot this point. E to the 24th is massive. I'd have to go. So pretend I'm doing it. The z-axis is going beside me. And then, ta-ta, I plot that point right there. That's in the what of the function? That's in the what of the function? Range. But the point on the graph of the function would be I'd come over here, go straight up there, and plot that point up here. Is this making sense? And so what we see is, I don't know why I think if I yell it, what we see here is when we're thinking about functions with more than one dimension in the domain, specifically 2, the graph of it, if I plot it over the entire domain, imagine that I plotted all of the points in the domain of this, and I looked up, what would I see? If I plotted all the points in the domain, imagining my floor is the domain, and looked up, what would I see? It wouldn't be a plane, but it's almost like a space sheet. And don't change it to an I, okay? A space sheet, because in the first class it came out as space, not a good word, okay? Like you get a space, and then somehow the E didn't come out, and it came out as it. And then I'm like, what did I just say? You know, space sheet. Okay, so if I plot it in the domain, I get this space sheet going above my head. Or going down through the floor. Does this make sense? Does this make sense? Okay, so like for example, this is kind of fun. If I say f of xy is always the constant 4, f of xy is always the constant 4, is there any problems with the domain? Is there any problems with the domain? Is there any division by 0 with that puppy? Is there any square roots of negatives? No natural laws. The domain's all x, y. What's the graph of this look like? What's the graph of this function look like? What's the space sheet look like in the room?
It's flat.
It's flat. Rough 4. It's going right through me. Does this make sense? Does this make sense? Okay, so now what I want to do is I want to plot some space sheets. I want to plot some space sheets. Are you willing? Are you ready to go with me? Are you willing to do this? Okay, so what I want you guys to do, I'm going to go share my screen. I'm going to go share my screen. Okay, you guys just look back this way. And you guys who are watching on the video on my phone right now, I don't want to hit it. Sorry, you're out of luck. You should be in class. You should be in class. Okay, so let me go here. Can you guys hear me okay? I know I'm kind of in a tunnel, but can you still hear me? So I'm going to share my screen. This is just our plotting program, and let me get rid of this. Okay, so here's my function. My function of x and y is what? Can you guys help me out? Read that to me. What is that? Z equals this function of x and y. It's 7x times y divided by
E to the 2 squared
x squared plus y squared, and then plus 2. Okay, now if I plot all the points where my domain is, x is going to run between, my domain is x is going to run between -2 and 2, and y is going to run between -2 and 2. Now what would that look like on the floor? What would that look like on the floor, guys? If x is going to run between -2 and 2, and y is going to run between -2 and 2, what's that going to look like on the floor if you're looking at all the points that satisfy that? A square, yeah, a square whose center's at the origin. And then if I plot all the points, this is the space sheet we get. I almost said it again. This is the space sheet we get. Is this pretty cool? Is this pretty cool? And so what it's like we're doing, this would be kind of our view underneath it. This would be kind of our view underneath it. Now if I remove this +2 and plot it again, what just happened? What just happened with that space sheet?
Shifted down to.
Yeah, it shifted down to, and if I put a -2 instead of +2, do you see how that shifts it down? Do you see how that shifts it down again? So now it's almost like, if I'm looking in the domain, now I'm looking down on this thing. So you guys give me a function of 2 dimensions. Give me a function of 2 dimensions, and let's just plot it. Give me a function of 2 dimensions. What do you guys want? This is a delaying tactic, isn't it? Give me a function of 2 dimensions.
X cubed, y squared.
X raised to the 3rd times y squared. Is there any problems with the domain of this function, guys? Is there any troublemakers on the floor? No. So let's plot this thing and see what it looks like. Whoa, Michael, look at that puppy. Look at that puppy. Okay. It almost looks like a saddle, doesn't it? I mean, it looks like he made a chair, a modern art chair there. Okay, so we've got that. A little uncomfortable, maybe. Actually, it looks like some kind of male support. Sorry. Okay. Give me another function. Oh, stop. Okay. Give me another function. Give me another space sheet.
Can you do the same thing divided by xy?
Ooh, I can. Okay. Ouch. This is gonna hurt. What's your name again?
Sean?
Sean, thanks, Doctor. So x times y. Oh, Sean. Okay. Guys, now, is there some problems now, guys? Is there some problems?
Yeah.
We don't want x times y to be equal to 0. We don't want x times y to be equal to 0, which means x can never be
0.
and y can never be
0.
0. So we can't have anything on the x-axis and the y-axis. Does this make sense? Or it's going to cause division by 0. So Sean, I expect some pretty nasty behavior along those axes as this program tries to plot, does its best to plot essentially those vertical asymptotes. Oh, you piece of crap. Oh, that's not even close to what that looks like. Did I get divide right? That's the right symbol for divide, right?
Yeah.
Oh no, it's actually, you put in a removable singularity there. You put in a removable singularity. Because if we take the x into the x cubed, we get a x.
Square.
And you take a y in there, you get a...
Y.
Yeah, they should not have anything plotted. They should not have anything plotted along the axes. It's a removal. So now I'm going to change this to a plus just to piss it off. Okay, now is there some problems? X plus y can never be
0.
0, which means y can never be equal to
Negative x.
negative x. What's that look like? What's the graph of y equals negative x look like?
A line.
A line. So if I draw the line y equals negative x down here on the floor, this thing should hate that. And now that's more like what I wanted to see. Okay, now you can see everything looks pretty cool, except as we hit this line y equals negative x, it's like saying I punt. It's saying I give up on that line y equals negative x there. I give up on that line y equals negative x. Is this making sense? I mean, visually, can you guys now see this a little bit better? Okay, let me stop sharing. Okay, so now what I want you guys to do is do your best to graph what's not allowed in the following function. Okay, I'm going to give you a function, and you guys do your best to find the domain of this function. Okay, here's your function. It's f of xy, it's z equals f of xy is equal to x over y minus x squared. Do your best to try to find what values down on the floor won't be allowed into your function. And again, for you guys at home, it's f of xy equals x over y minus x squared. Try your best to graph Okay, you guys help me out for a second time. Who's not allowed? What would be bad? What would be bad with this function? What would be bad with this function? If y minus x squared is ever one number, that would be bad.
0.
0. So let's just say y minus x squared we don't want ever to be 0. So let's find out when it is 0. Okay, now, what do you think you're going to do next? What do you think you're going to do next? What do you think you're going to do next? How many people could at least get there? How many people are like, Dr. Warren, I think I could follow that? Now you want to go back to something that you know in high school. Well, if y minus x squared is 0, then y would be equal to
X squared.
x squared. Now are you back to a shape you're familiar with from high school? Now are you back to a shape that you're familiar with? This is the graph of a what? Parabola. It opens up the x-axis or the y-axis.
Y.
So try to draw that down there on the plane. Do your best to try to draw that down there on the plane. Because those are the points you're going to kick out of your, those are the points you're going to kick out of your okay, this is which axis, guys? This is which axis? This is which axis?
Y.
And this is my range, these are my two domains. Now I'm gonna have a parabola. Is it going to open this way or that way? Is it gonna open this way or that way? That way. It's gonna go like this and like that. So this is the graph of y equals x squared. So my domain is everybody in the xy plane except the ones on the, everybody in the xy plane except the ones on the parabola. So let's go take a look and see what this looks like. And see if we can see that. Okay, you guys tell me what to do. What should I do now? What should I do now? You tell me what to do. What do I do next if I was trying to use this plotting program? What would I do next? And what is my function again, guys? What is my two-dimensional function? Divided by y minus x raised to the second. And we expect problems along that parabola. Okay, so this is what I've got here. This is my x-axis, this is my y-axis. And do you see here, if we shoot down here like this, do you see how we're having problems along that parabola? Do you see, I can't quite get it lined up, but do you see how we're having problems along that parabola there? Guys, imagine teaching a grid and humans at the same time, and then realizing also people are going to be on the camera at another point in time. And I'm ADD, so I just want to, I'm so used to teaching people in my class that, sorry guys, I sometimes forget about you in the grid, and it makes me feel guilty later, okay? It's like my children. You know, no matter which child you're actually investing into, you feel guilty about the other child. And guess what daughters do? They make you feel guilty. That's one of their gifts. That's one of their gifts, is making you feel guilty. It's the gift of a daughter. Sorry. All right. And when you got 5 of them, I just live in constant guilt. And this isn't talking about the wife. I mean, oh my gosh. Can you imagine that too? I mean, imagine my life, guys, really. I just feel like a Sherpa. That's what I feel like. My life is a constant Sherpa. You know, the drone bee. Kill it. Okay. You're done having 5 daughters, kill it. Tell me this. I mean, I'm sorry guys, I know I'm gonna make somebody mad because I'm old. But everybody's like, you know, Dad, you're a chauvinist. You can be chauvinist sometimes. I'm like, guys, I don't feel like I'm a chauvinist. I'm aware, and they're like, no, Dad, you're way out of whack. You're 60 years old, you know. And I'm like, okay, then why is it every time the refrigerator needs moved, Dad's the one who has to do it? Nobody else is up there helping me. Anytime there's something to lug, you know, nobody else is helping me in the family. Oh, sorry, let me just move the refrigerator. I'm like, where are the girls? Where are these girls, these empowered women? Where are they to help me? Sorry, it's just one of those days. Okay.
Is there only one problem?
Only one bad parabola. Oh, yes. Sorry, Michael. Michael's like, hey, Dr. Warren, you're teaching, remember? This isn't therapy for you. Okay. This is where I was going. Guys. Okay. This is cool. I mean, sorry, isn't this cool? I mean, think about this. Has this opened up a new world to you? Space. Say it. I'm not going to say it wrong. We've got the whole new world of space sheets that you didn't have before. Now imagine that you're thinking about a function that depends on more than one thing, and imagine this represents profit. Imagine that represents profit. What are some things you'd like to know? I mean, like if you're thinking about a function and it represents profit, it's some model that represents profit. What are some things you'd like to know about that function? I told you we have no business majors. Okay, so imagine it represents stresses. Imagine this represents stresses on a beam. What are some things that you might want to know about this function?
Maximum stress.
There, where's the maximum stress going? Does this make sense? Where's the maximum stress going to occur? Where's the minimum stress going to occur? Does this make sense? When is the stress increasing? When is the stress decreasing? Well, what tool from calculus helps us answer those kind of questions? The derivative. And you're like, well, Dr. Warren, what the hell does a derivative mean for a multidimensional function? And guys, you don't want to know. You don't want to know. What does the derivative mean for a real valued function? If you say slope at tangent line, I'll vomit. Okay? What's the definition of a derivative of a real valued function? What's f prime of c?
The limit.
Limit as x approaches c of
F of x minus c.
all divided by,
X minus c.
I mean, is there division by zero? Is there division by zero? Is there potentially division by zero as this limit goes to c? Do you see the troublemaker?
Yeah.
And you're like, well, Dr. Warren, what is the natural extension to two-dimensional space or three-dimensional space? Calculus is about, calculus is about, calculus is about, calculus is about, calculus is about limits, derivatives, and integrals. Oh my. Guess what? It's going to be defined in terms of a limit. Now let me just show you the limit. Let me just show you the limit. Be afraid. Be very afraid. Okay. F is differentiable at x equals a, and we'll just do this in any dimension. This could be n dimension. We'll just keep it. My domain is multidimensional. In this class, this will always be xy. This will always be a1, a2. If and only if the limit as x approaches a of f of x minus f of a. How many people are pretty comfortable so far? How many people are pretty comfortable so far? Okay. Now this is where all. Now, what do you really think should go on the bottom? What do you really think should go on the bottom? If you had to guess, what do you really think should go on the bottom?
X minus a.
X minus a. Okay. Now, why can't we have an x minus a? Why can't we have an x minus a down there? Well, Dr. Warren, you can. Because these are vectors. What's 1 over a vector? Have we talked about that? Have we talked about vector division? Have we talked about vector division? And you want to know why? Because it doesn't exist. Okay? Gibbs threw it away. Gibbs threw it away. He didn't teach the quaternions. We have what products? What are our products? Cross, dot, scalar. No division. And that's when you realize, oh hell, this is going to be a lot harder. But I can do that. Can I not? Can I not? That would talk about the norm of x minus a. We can talk about that, because that's just a real number. Does it capture the division by zero? Does it capture the division by zero in some small way that we have over there with our regular definition? Okay, now here's the thing. We can't say this goes to a vector. What we say is it goes to zero. And then up here, we need to put our derivative, and we typically call it d. But now everything's screwed up, because this is a vector, this is a scalar, this is a scalar, it's what's coming out of the function. This is a scalar, and so we dot it with x minus a. There's the definition of the derivative in higher dimensions. You never knew how much to appreciate the one single dimensions. Now, of course, we haven't defined that. Calculus is about limits, derivatives, and oh my. And now you're going to understand the oh my. So stand up and get ready to be oh my. Stand up and get ready to take your oh my. This is the hardest part of the class. The definition of the limit in higher dimensions. Oh, here we go. Does anybody remember the definition of the limit in lower dimensions? Does anybody remember the definition of the limit in Calc 1? Very good, Caitlin. Come on up here, Caitlin.
Oh, no.
Come on, Caitlin. You stand in front of the camera, in front of your class. The limit as x approaches c of f of x equals L, if and only if.
For every epsilon greater than 0, there exists a delta greater than 0. Such that if the absolute 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon.
Let's give it up for Caitlin. The first 237 student to pull that out. The first 237 student to ever pull that out. Wow. Okay. Yeah. So let's write it down. Holy hell. I mean, if you're going to say it, so we would say the limit as x approaches c of f of x equals L, and then she said, if and only if for every. This is where you start appreciating these symbols. Imagine writing for every. Epsilon greater than 0. Now, anybody from 235 who's done this suddenly has like cold chills running down their spine, like, woo! But it's Halloween, right? Shouldn't we be afraid? I mean, this is the perfect time to introduce this. There exists. That's what that letter means, that backwards E. There exists. It's just shorthand. There exists. I'd rather write this than the words there and another word called exists. The limit as x approaches c of f of x equals L, if and only if, for every epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus c is less than delta, absolute value, what did they attach that to in grade school? Absolute value, what did they attach that to in grade school? Elementary school, sorry. Do you guys remember it was attached to distance? You guys remember that they attached to distance? We're saying if the distance between x and c, if the distance between x and c is less than, if the distance between x and c is less than delta in the domain, it must logically follow, you're like, oh, there's another absolute value. Well, again, it's going to be distance. Then the distance between f of x and L must be less than epsilon. You guys see these, but you never remember how to do them. Okay, I've got the absolute value of x minus 2 is less than 5. And remember they said find all the x's that satisfy that. Do you remember doing problems like that? Find all the x's that satisfy that. So go ahead, find all the x's that satisfy that. You guys do that at your seats. You've been watching me work. You work. Find all the x's that satisfy that. Okay, let's go back to elementary school. We have an interval, What are the x's that satisfy that? Well, what's the lower number? What's the lower number? -3. Then let's go back. Remember the filled in and empty circles? Remember that game, filled in, empty? Would it be filled in or empty?
Empty.
Empty. And then what's the upper number? What's the upper number? 7. And then we draw the line between. Now, who's in the middle of this interval? Who's in the middle of this interval? Okay, yeah, there would be an x in there, but like, who's in the dead center of the interval? What number's in the dead center of that interval? 2. What's the distance between 2 and 7? What's the distance between 2 and -3? 5. So it's all the x values, focus, it's all the x values whose distance from 2 is less than 5. Okay, so now what are we talking about here? Just ignore that dude for a second. What are we talking about here? All the x values whose distance from C is less than delta. So this would be C plus delta, and this would be C minus delta. And I'm going to pick an x value in between these two. Now what about that dude? You know, Dr. Moore, come on, man. Absolute value is always positive. I'm like, well, wait a second. What's the absolute value of 0? What's the absolute value of 0? 0, so it's not always positive. It's mostly always positive. What's the only value of x that would violate the greater than 0? What's the only value of x that would violate the greater than 0? C itself. So the only difference between this and this is right in the middle we have a puncture hole. So graph this. Graph that. Graph the domain. Sorry, it's going to be the domain. Graph that interval. Okay, go to grid view, guys. Go to grid view and hold up what you have. Go to grid view, and you guys look around here. You guys see if you got the same interval. So you guys go to grid view and show me what you've got. I'm back here. I'm back here with you. I'm back at the screen. Show me what you got. Can you see what you guys have? There's nobody holding up anything. There's nobody. Mason, what do you got there? What do you got? Nice, Mason. Nice. Emily, what do you got? Yeah, I think that's right. It's a little blurry. Rachel, what do you got? Thanks, Greer. Just hold it really still there. Okay, awesome, awesome, awesome. Okay, so I think we're seeing lots of good things. So you guys help me out. What did you have? What did you have? What did you have? What would be, who's in the middle? Who's in the middle? Who's in the middle?
4.
4. What's this endpoint? 11, up 7, and then we would draw a hole. Anybody get that? Anybody get that? Okay, so let's do the same thing over here. And like, I hate you, Dr. Warren. Let's do the same thing over here. This would mean that f of x would be between where and where? This would mean that there's no 0 here. This would mean that f of x would be between doing the same kind of game. It's again, it's an absolute value inequality. F of x would be between,
L plus epsilon and L minus epsilon.
very good, Rhett, L plus epsilon and
L minus
L minus epsilon. You're like, Dr. Warren, is that it? No, guys, this is the limit in one dimension. We're talking about the limit in 2 dimensions. Now give me that deer in the headlight look. Give me that deer in the headlight look. Okay, now I'm going to write down the definition in higher dimensions. And then we're only going to go to 2 dimensions for our domain. Here we go. For better or worse, here we go. Oh, you better stand up. This is going to just be a beating. Stretch. Because when you first see this, you're like, I'm never going to understand this. And my goal is by end of class, you're going to at least understand it a little bit. Yeah, good. Okay, so here we go. Oh. This is the definition. How many people are pretty happy so far? How many people are pretty happy so far? I mean, like, you're like, limit, Dr. Warren, we're good. Okay, okay, now my domain ain't X. My domain is like XY, or XYZ, or XYZ, I've run out of letters. XYZA, XYZAB, I've run out of letters. Okay, but we'll typically just use a vector notation to represent there's more than one. There's more than one. The limit as the vector x goes to the vector a. So this is kind of like that guy. And the a is kind of like my c. Of f of x equals L. Now again, this is a real valued function, so I only get a real number out of it. I plug in more than real numbers into it, but I only get one real value out of it. Equals L. So this L could be the same as that L. If and only if. Are we pretty happy now? I mean, we're pretty happy now as far as we're read. For every, and what do you think is going to follow that? What do you think is going to follow that, guys? What do you think is going to, for every epsilon greater than 0, there exists a delta greater than 0. What do you think is going to follow that? What do you think is going to follow that, guys? Is I erased it such that. That's laziness. S dot T dot such that. How many people are beginning to like not having to write the word for every single? And this word means there exists. This is just, it's just a variable. I've been tempted to change it to smiley face and ice cream cone, but then you would hate smiley faces and ice cream cones for the rest of your life. You would never eat another ice cream cone. So I just like figure, let's just leave them as these little devil animals, epsilon and delta. Because the moment you see any Greek, you think you're never going to understand it. The moment, it's Greek, theta, alpha, oh my gosh, I'll never get it. What is this? Epsilon, and what's that? Delta, okay. So, such that, now, down here there's an implies. Down there there's an implies. How many people would expect the implies? How many people expect the implies? And then over here, we get an absolute value. Are you guys comfortable with that? Are you comfortable with that? And then over here, we have an epsilon. You're like, hey, Dr. Moore, this ain't so bad so far. Now over here, we've got a minus L. You're like, Dr. Warren, things are looking good. What do you think goes there? What do you think goes there? F of now not the variable x, but the vector x. Okay, now, let's come here. We're saying 0 is less than the absolute value of x minus c is less than delta, but now x is a, and a is a, how many people realize no absolute value? How many realize absolute value is out? How many people realize, what's the extension of distance to vectors? The norm, and that's where we go. If and only if, for every delta greater than 0, such that the norm of x minus a is less than delta, and again, over here, we had the definition of the derivative. What was in the bottom? Does anybody remember? I don't think any of you remember. What was in the bottom of that definition of the derivative? Don't you look at your notes. What was in the bottom of that definition of the derivative in higher dimensions? The norm of x minus a. As x goes to a, what happens in that denominator? As x goes to a, what happens in that denominator if you've got the norm of x minus a? It goes to 0. So we're going to have trouble at 0. We're going to have trouble at a. And so we kick a out, just like what we did in our other one. Okay, so now read the definition. Now read the definition to me. Definition of limit in higher dimensions is the limit as x approaches a, but now they're vectors, of x equals, if and only if, such that implies that the absolute value of f of x minus L is less than epsilon. I had the student do the nicest thing for me this semester. He sent me a picture, and I'm flattered, but also a little concerned. I'm flattered, but also like, he sent me a picture of his arm. And on his arm, he had tattooed that. I mean, it's like, wow. That's really great. I mean, I love the fact that, but then I was like, but that's on you forever, man. That's really, I mean, I'm like, okay. Then it was kind of like, am I going to have to do the same thing now? Like, is this going to be like Brother, kind of like a new club that we're creating, the Limit Club? Like they have the 7 Club over at UVA. Maybe this is the new donation club, the Limit Club, when you're all wealthy later. Okay, we all have this tattooed on our bodies. Okay, so no, but I mean, guys, really, when you go home for Thanksgiving break and never come back, okay, sorry. I mean, when you can never come back this semester. When you go home for Thanksgiving break, and your parents ask you what you did in 237, just pull that out. Lay it in front of them. And just watch the deer in the headlights. And then they'll respond with, oh, that's really nice. That's really nice. And then you read it to them. You're like, this means the limit as x approaches a equals L, if and only if. And you just start reading and just watch them. It's almost like at that point in time, you could take a scalpel and just start the operation. You know, they're so gone. They're like, they say they want to know what you're doing, but they don't. You can tell they don't. They just want to believe it. They're like, what are you doing? And then you start telling them, and they just start going, ooh. And then you stop and they're like, oh, that's nice. And then you want to give them a test. Here's a quest for you. What does this symbol mean? And then they would say nothing, and you would say that means. What does this symbol mean? What is this symbol? What's this symbol? What's this symbol? No, okay, good, okay. So now let's try to unpack this a little bit. How many people can say it? How many people can say it? I see nobody in the grid. How many people can say it? Raise your hands. Rachel, you can't say it? Oh, there we go, good. How many people can say it? But how many people, when they hit this point, just start zoning? Their brain just starts shutting down. How many, when they hit that part, they just start shutting down? Okay, so let's try to unpack this. We're only going to be concerned about it. Stand up. I can tell already. I just felt the board going around like an evil spirit. You guys need it at home more than they need it here. I'm spitting on them. Well, actually, I'm spitting into a mask. This is the first semester I haven't spit on people. So by mistake. Sit back down, sit back down. In this class, guys, we're only going to be concerned with this. Because if we can't understand it with 2 dimensions, we're done, we're toasted. We can't even graph X, Y, Z. Okay, by what we just did with the graphing program, when you plot this thing on its domain, what do you get? When I say f of x, y, what do I want you to visualize? When I say f of x, y, I want you guys to say space sheet. When I say r of t, I want you to think space curve. When I say a plus td, I want you to think line. When I say n dot x minus a equals 0, I want you to think plane. Okay? But when I say z equals f of x, y, I want you to think space sheet. Now, what test did you use in high school to determine whether or not it was a function? Their vertical line test. There's another similar kind of test that you can use for space sheets. If the space sheet, I'm using Trevor's quest here, if the space sheet ever bends over itself like this, do you guys see how that would violate it being a function? Do you guys see how that would violate? Because down here on the floor, there would be 2 different z values for one x, y value. Does this make sense? So it's still kind of like a vertical line test, except it's shooting off the floor through this. So now, I'm going to draw a space sheet. Give yourself an XYZ. Give yourself an XYZ. You're going to draw with me. Give yourself an XYZ. Now, space sheets are a little hard to draw. See, this is what stinks about COVID. Normally, guys, what I have is all of you guys in class, because I have that horrible attendance policy. There'd be 35 people in this class, and I bring in a tarp into the room. That's what happens. And I have kids hold the corners of the tarp, and then we wave it up and down so they can see the space sheet moving. But now I just got to draw the space sheet. So what I'm imagining is I've got this tarp kind of floating above. I've got this tarp kind of floating above my XY plane. And this is just like a chunk of my space sheet. This is just like a chunk of my space sheet. How many people right now are happy we don't have any division by 0 in this space sheet? How many people right now? How many people if it wasn't continuous, would that make this even harder? If it wasn't continuous, we're not going to understand. If we can't understand this for continuous functions, we're screwed if we head to differentiable functions. Okay, so now, let's go back and start unpacking this. The limit as, but these are not scalars, they're vectors. It's okay, I'm in 2 dimensions here. So I've got a vector A, and it just has 2 components. It's not a 3-dimensional vector. It's just down here in the plane. There's an A1 and A2. So draw a vector, draw a position vector down there. Draw a position vector underneath your space sheet and mark it as A. Draw a vector down there in your XY plane and mark it as A. And I'll do the same. I'll do the same. So imagine that this is my A. It's down here on the floor. It's down here on the floor. And I'm going to draw that to that point. This is my vector A. And so this point down here in the xy plane would have what coordinates? This point down here in the domain would have what coordinates?
A1 and 2.
A1, A2. Now let's plug this in. Plug this point into your function. Plug your point into your function, because that's going to kind of like be my L for this. So how would I plot this point? How would I plot this point? What do I do? I'm here. Now what do I do? What do I do? How do I plot the point? What do I do? Go straight up, and this is where it's much easier when there's actually a tarp in the room to go straight up. But now imagine that I'm going straight up, I'm going underneath the tarp, and I cut that tarp right there. Now what do I do? Now what do I do? Since it's z equals f of xy, now what do? Very good, Stuart. Now I head back here to the z-axis. And this is like my z equals f of a1, or to write it simply, f of a. How many people are following so far? How many people are following so far? Okay, this value back here, what did I just say? For what we're trying to do is going to be our L. So mark that as L. Mark this L on the z-axis. This is like my L. So that point's like my L. So mark an L, guys. Mark an L right there. Okay, so now we're saying, read this to me. Read this to me.
0 is less than 1, x minus a is less than delta.
And you're like, oh. Okay, so read this to me. The limit as x approaches a in the domain, then f of x approaches L in the range. Now this is where kids don't get it. What did I just say? Sorry. This is where the wheels fall off. And I can see in the grid, only Cosmo's with me. Only Cosmo's. Zach, I've about punched you to death. Sorry. Emily, are you with me? Are you with me, Emily? Okay. When you explain this to somebody, you're saying, well, the limit as x approaches a. Now they go, what does approach mean? And you're like, what aren't you getting, man? Okay. Let me explain it to you a little differently. As x gets closer and closer to a, f of x is going to get closer and closer to L. You're like, okay, as x gets closer and closer to a, f of x is going to get closer and closer to L. But then we remember the horror that math is. We remember the horror that math is prove. You've got to prove stuff. Give me a good definition of closer and closer. A good mathematical definition of closer and closer. I mean, that's just such a vague idea. Well, Dr. Warren, here you go. You get closer and closer. My guys, you're stepping on the floor. That can't be a mathematical definition. What do you mean gets closer and closer? This is as good as it gets. This is the definition of. This is the definition of closer and closer. Do you want to talk about the definition of limit? We can also call it the definition of, the mathematical definition of closer and closer. Right? This is the definition of closer and closer in higher dimensions. Like, I don't like this document. I don't like closer and closer. No, I don't. But find something better and I'll go with it. Find something better that works mathematically, that we can prove stuff with, and I'm with you. I'm going. Okay. So we need a vector x. We need a vector x, right? So let's put that in the game. Give me another vector in the domain and mark it as x. Give me another vector in the domain and mark it as x. Okay, and I'll do the same thing. Okay, so we're interested not in the vector x, but we're interested in taking the norm of the vector
X minus A.
x minus a. So draw the vector x minus a. Draw the vector x minus a. Like Dr. One, I forget how to do that. Draw the vector x minus a. You can do it. If you're drawing the subtraction vector, you do what with the two heads of the vectors? If you're drawing the subtraction vector, will you do what with the two vectors, the heads of the vectors you're subtracting? Connect them. So let's just connect those. Which way does the direction point? Which way does the direction point? Does it point towards A or does it point towards X if you're doing X minus A? X. So this is the vector X minus A. So we're saying as long as the norm, as long as the distance of the vector X minus A is less than delta, then f of x minus L better be less than epsilon. This would mean, let's see if you remember anything, I've erased it, I hope. And now I'm going to look over there and I didn't erase it, did I? This would mean f of x is between what two numbers? This would mean f of x is between what two numbers? L minus epsilon and L plus epsilon. So graphically, L plus epsilon and L minus epsilon are where in the figure? Graphically, L plus epsilon and L minus epsilon are where on the figure?
On the z-axis.
On the z-axis. So imagine that I've got an epsilon. Imagine that I've got a positive number. I come up here. That would be the point. That would be the point
L plus epsilon.
L plus epsilon. Epsilon's like this distance. This would be the point. That would be the point
L minus epsilon.
L minus epsilon. And what we have to find is for every, you pick an epsilon, I have to choose a delta, so that if this is true, this is true. I've got to pick a delta so that if my x is a point where the distance is less than delta, the corresponding value f of x must be caught, if we're using baseball analogies, because the Dodgers just won, and the Rays just lost. Okay, the f of x must get caught in the catcher's mitt, L minus epsilon and L plus epsilon. If I throw an x whose distance from A is less than delta, the f of x up on the space sheet must be caught between L minus epsilon and L plus epsilon. Now here, this is what we're heading towards the end, because I need you guys to understand this. What are all the points whose distance from A would be less than delta? What's the shape of all the points down here in the plane whose distance from A would be less than delta?
A circle.
A circle whose center is A, and whose radius is delta. So let's try to draw that. So let's draw a circle. Let's draw a circle. The radius of this circle is delta. The center of the circle is A. And if I pick any x in the circle, another x, I pick x in the circle, where does f of x have to fall? Where does the corresponding range value? If I come up and go over, where does the corresponding range value, f of x has to fall? In between the L minus epsilon and L plus epsilon. You know, Dr. Warren, how's that possibly even explain closer and closer? Say that. Nick, I heard nothing.
I missed the last part.
Closer and closer. Say, ask Dr. Warren.
How can it be closer and closer?
How does that capture closer and closer? So ask me again and I'll tell you. And I might even shut class down. Okay. You're like, Dr. Warren, closer and closer. What does that capture? Closer and closer. Let me go. Please let me go. It's all here. What's that word? For every. Give me an epsilon. There has to be a corresponding delta, where if this is true, this follows. Right now, epsilon's that big. Right now, epsilon's that big. If I shrunk it quite a bit, so that that was L minus epsilon and that's L plus epsilon, what's going to have to happen down here with this circle, guys, if we're going to meet the definition? What's going to have to happen? The delta's going to have to shrink. And I'm like, okay, well, Dr. Warren, that's pretty small. And I'm like, oh no, we're not done. We can go smaller still. And then what has to happen down here with this circle? And I'm like, we're not done. Dr. Warren, that's too close. No, it's for every. And you're like, well, how about epsilon equals 0.00000001? Well, there has to exist a delta. It might be so small we can't see it. But for all the x's I pick in that circle, where would the f of x has to fall? Okay, so guys, this is it. The way we say it is wrong. The way we say it is wrong, but we'll keep saying it that way. It's not as x gets closer and closer to A. It's really more like you're working in a factory, and you're saying you want your output error to be in a certain tolerance. There's some output error. Make the tolerance as tight as you want. I can come over here and make a tolerance down here, where as long as you stick in that tolerance, you'll be fine. You pick your x's within this tolerance, you know, the forces on the beam will fall within what you want up here. Does this make sense? But that's not the way kids learn about it. They're like, okay, well, as x gets closer and closer to C, over there in the range, f of x gets closer and closer to L. And I agree, guys. I agree. If the limit exists, yes. If it meets this definition, yeah, you drive in that way, you're gonna reach L. But that's not the definition. The definition says make your tolerance as tight around L as you want. There's going to be some delta around C which is going to meet that tolerance. Is this making sense? You're like, Dr. Warren, how can we prove anything with this? We don't. We don't. You're like, oh, good. There's a theorem that saves our rear end. How many people like theorems? Guess what? We're not even going to prove the theorem this semester. You're like, Dr. Warren, it's not going to be on the quest? No. Is the definition going to be on the quest? Oh. You mean the next quest? Oh. Okay, all right. Keep doing your homework. You have what due on Friday? WebAssign, which will also help you get ready for your quest.
Have a good one.
Thanks, David. Oh, I miss the days when my metabolism where I could just like say saying expressions like no fat, put it back. That was my saying. No fat, put it back. Not anymore. See you, Stuart. Thanks for class. Oh, thank you guys. Thanks, Red.
Thank you, Dr. Warren.
Oh, thanks, Caitlin.
Can you tell tonight what I said?
I will tell her. She will be so. Caitlin, I have never had a student do that.
It was because of her. I had her
Like,
for 2 semesters,
that's
and
so-
she just drilled it into me. So
Raylan, I don't know if you've ever seen that. So yeah, this is brand new. But you were doing well. You were hanging.
thank you, have a good day.
See, guys, you two have seen it. I don't know if you've ever seen it before. the delta epsilon definition.
Oh, yeah.